Okay, thank you, Liang. So I also want to thank the organizers for giving me an opportunity to give a talk here. So today I'm going to talk about how to encode an oscillator into many oscillators. So here's a brief summary of what are the various types of QEC. So are the most popular and the most standard way to implement quantum error correction is, of course, using the qubit-based QEC, where we take many noisy physical qubits and then sacrifice some of it or most of it to define fewer but much better, much less noisier logical qubits. So that's the standard way of doing things. And recently there has been a growing interest in using a bosonic system to do error correction. So in this specific case, we take an infinite dimensional physical oscillator, and then we take this infinite dimensionality as a redundancy, and then we sacrifice most of the levels, and then we just choose to protect this two-dimensional subspace very well. So that's the usual way to do a bosonic QEC. Today, I'm going to talk about yet another type of bosonic QEC, where I take many noisy physical oscillator modes, and instead of just protecting a finite dimensional subspace, I'm going to protect an infinite dimensional oscillator mode. So in this sense, I take many bosons and then make a better boson out of it. So that's what I'm going to do today. So before going to that, why do I want to do this bosons into bosons? The reason is, if we take this usual way of doing bosonic QEC, where we encode a qubit out of the oscillator, then although our native physical system is bosonic in its nature, the outcome in the end is a qubit. So if we imagine using this kind of code for, say, continuous variable task like boson sampling or simulation of bosonic systems, we basically started with the bosonic mode, which was suited for this kind of purposes, but then what we get at the end of the error correction is not anymore tailored to this kind of application. So that was the reason for me to think about how we can encode a boson into many bosons, so we can directly use them for such a purposes. So that was the motivation, and before going into any more details, I want to just briefly recap the stabilizer codes, because it's relevant. So here, stabilizer codes basically include almost all interesting qubit-based quantum error correcting codes. And the idea here is that we take this data qubit, and that's where our quantum information is stored. And then we introduce this redundant ancillary qubits, which initially was prepared in the computational zero state. And then we let this data entangle with the ancillary through some Clifford operation. So this turned out to be a really nice framework of defining a error correcting code, because unless we want to implement some non-Clifford gate, if we just want to correct error, it turns out that stabilizer states and Clifford operations and Pauli measurements are sufficient to do to correct some relevant errors. So everything was really nice, and the fact that those Clifford resources are sufficient kind of allows us to simulate the error correction procedure just by using Garesman-Kneel theorem, and we can very efficiently simulate the error correction procedure, especially when we assume depolarizing noise or some random Pauli noise. So everything was really, really nice with this stabilizer code. And also, I should remark that any logical Clifford operation can be implemented by just physical Clifford operation. So everything is really nice with this stabilizer code. So everything was really good here. Now, moving on to bosonic system, for 1 second, let's think about a hypothetical situation. Let's be just a little imaginative and think about the following hypothetical situation. A really bad situation, actually. So a situation where we have Pauli errors, and then Clifford operations are not enough to correct them. So in other words, let's think about a situation where stabilizer codes cannot correct Pauli errors. Can you imagine how terrible that will be? Unfortunately, that's the situation which bosonic QEC community is facing every single day. So it turns out in the bosonic case, we have Gaussian errors, as we will see, which include kind of random Pauli error. And it turns out that if we only use Gaussian operations, which directly is translated into Clifford operation, it turns out that we cannot correct errors, the Gaussian errors. And this is really problematic because Gaussian errors include photon losses, heating, and additive Gaussian noise error. And especially the additive Gaussian noise error is kind of like a random Pauli error. So this no-go theorem is imposing a really hard limitation on the practicality of Gaussian error correcting schemes. So it means that if we define bosonic code by directly translating the stabilizer code into bosonic systems, we end up getting some Gaussian error correcting scheme, and by this no-go theorem, it cannot be useful. So what I'm going to do in this talk is I want to show how exactly these bosonic stabilizer codes, which are implemented by Gaussian operation, exactly fail, and then I want to identify where we started failing, and then we want to fix it. So here's the first indication that bosonic code might not be very good. So as we all know, these standards like stabilizer codes, say 513 code, Steen code, or Shor code, they all are very great because we can correct arbitrarily single qubit errors. And that's a really relevant thing to do in the qubit case. But then we can also define an analogous type of bosonic code, which is just direct translation of these stabilizer code, and we can define such a Gaussian code. And analogously, it can also correct arbitrarily single oscillator error. So it might sound like very good thing to have, but from now on, I'll show that this is not as good as it might sound. So to make the discussion more concrete, I'm going to consider this additive noise error, which one can kind of think of as random Pauli error, because what this additive noise error is doing to my bosonic state is that it's gonna induce some random displacement error, and displacement error is kind of like a Pauli error, so it's gonna add some noise to my quadratures. So that's the error model that I'm considering, and with this error model in mind, let's go back to the qubit case and let's compare how qubits are different from bosons. So in the case of qubit, if we have a very decent high quality qubit, very likely we don't have any error in our system at all. And then with a very small probability, we have some error, let's say with 1% chance. So the situation here is very likely if we have a very distant set of qubits, most of the qubits are not undergoing any error, and with some small probability, a single qubit is undergoing some error. So correcting this single qubit error is a very relevant thing in the case of qubit. But on the other hand, if we think about the additive noise with some random Gaussian distribution, the chance that, so if we have a better bosonic system, the distribution is gonna look a little sharper like this. But still, even though we have a really, really good bosonic mode, the chance that we don't have any error at all, which is just the chance that we are sitting in this exact zero axis, is 0. So what this means is, although we have a really, really good bosonic mode, very likely all of the bosonic modes are undergoing, although small, some error. So even if we correct a single bosonic error, it doesn't help too much because very likely all of the other bosonic modes are undergoing some small error. So instead of just focusing on correcting a single oscillator error, we have to be focusing on correcting small error for all of the bosonic modes. And the previous code, which was direct generalization of the 5-qubit code or Steen code or Shor code, didn't take that into account. So that's one of the high-level reasons why they failed to be useful. And I want to dive into a little more detail, and then I'm going to show how exactly, say, the repetition code fails to correct relevant errors. So in this case, this first mode is representing a data mode where my bosonic quantum information is stored. And then I'm going to introduce some other ancillary mode which are initially in the position eigenstate. You can think of this as a computational zero state. And what I'm doing next is I'm going to use a bosonic analog of the C0 gate. And then with it, I can define analogously a repetition code. And the error model that I'm assuming, again, is this additive noise error. So what it does is it's adding some stochastic random noises to my quadratures. So after this, the way the error correction works is because we encode it with this C0 gate, ideally, if we didn't have any error, and if we invert the encoding circuit, we are supposed to get back the position eigenstate in the ancillary mode. So if we just invert the encoding circuit, and then if we check whether we have the desired zero eigenstate here, we can if we don't have such a desired zero state, we know that there was an error. So that's the procedure here. So we invert the encoding circuit, and then we see if we get the desired zero state here. And if it's not, based on that, we can learn what kind of error happened, and we can correct the error. So that was the premise. And let's see how errors are propagating. So here in this particular example, I'm trying to keep track of the position quadrature noise, which is represented in the top part of this line. And then you can think of this as a Pauli X error. So due to the inverse C0 gate, the X errors are propagating into theta mode and also into the ancillary mode. So by measuring the position of the ancillary mode, we can learn something about the noise that we want to correct, and this is the part that actually works in this scheme. So based on this information, we can infer what the position noise would have been, and then based on that, we can reduce the noise. So that's the part that actually works here, and that's what we want to preserve later. Now, the bad part is we also have to consider, say, momentum error, which is kind of like Z error in the qubit. So C0 gates act differently on the Z error. So in this case, Z errors in the ancillary qubit is going to propagate to the data mode. So this is potentially a concern, and this is a real concern because the momentum noise here is going to be completely undetected. So this momentum noise can potentially damage the entire scheme. And as it turns out, what we have in the end is we are going to have some logical bosonic mode with some effective new random displacement error. And what I'm going to show you here is that whether the variance of this new effective stochastic noise is decreased or not. So as I explained earlier, we can learn about the position noise, and indeed, it's kind of like repeating measurement n times, and then with this repeated measurement, we can reduce the noise in the position quadrature by a factor of n. So that's the part that worked really nicely in this scheme. But unfortunately, because the momentum noises are gone completely undetected, we have some effective momentum noise, which is increased exactly by the same factor. So what we have at the end of this scheme is that we only squeeze the noise instead of correcting it. So we just define some other noise channel, which is equivalent to the one that we started with up to some squeezing. So we ended up not correcting the error. And this was proven in the most general detail by Christoph and Barbara Turner. So this is the situation we want to fix. So to fix it, let's think where things went wrong. And obviously, as I talked about, the situation would have been fixed if we can measure both position and momentum quadratures. Because the reason why we failed was because we didn't detect momentum at all. And unfortunately, it's the first thing that we learn in the quantum mechanics, that we cannot measure position and momentum simultaneously. But luckily, it turned out we don't have to measure position and momentum like entirely. We only want to measure small positions and small momentums. We don't have to measure, say, something that's far away if it's not something happening. So based on that kind of intuition, what turns out to be the case is, although we cannot measure position and momentum simultaneously, we can measure them simultaneously modular some number. Let's say in this case, square root 2 pi. So because displacement operators can commute, we can measure their exponent modular 2 pi, and therefore we can measure position and momentum simultaneously modular square root 2 pi. And indeed, the end result with this simultaneous position and momentum measurement outcome is the GKP state. And indeed, it has this desired property. And as we can see from the negativity in the Wigner function, GKP state is clearly a non-Gaussian state. And this non-Gaussianity is the way for us to work around the previous no-go theorem that says we cannot correct errors if we only use Gaussian operations. So here's my fix. instead of having position eigenstate in the ancillary mode, I replace that by a GKP state whose position and momentum are 0 modular square root 2 pi. So that's my first fix. And then later in the decoding procedure, instead of just using position homodynamic measurement, I replace that by simultaneous position and momentum measurements. So that way, I take care of both position and momentum. So indeed, as long as errors are small, we have the same advantage that we had from this position noise propagation, and we can therefore benefit the same way. And now, because we also keep track of the momentum noise, we are not anymore limited by the ancillary momentum noise that's propagated from the ancillary to the data. So the end result is, as long as the standard deviation is much smaller than square root 2 pi, which is the window that we can simultaneously measure, it turns out that we can keep the same advantage, which is suppression by a factor of 2, and then we are not anymore limited by the momentum noise transfer. So that's the key idea of this non-Gaussian quantum error correcting code. And here's the numerical result. So indeed, as the errors are small, we have the desired factor of square root 2 improvement in the position momentum noise, and we are not anymore suffering from the momentum noise propagation. So that's really good. And so if we take a step back and compare this with the Gaussian repetition code, basically I replace the position eigenstate with the GKP state, homodynamic measurement with the simultaneous modular measurements. So I basically replace Gaussian elements to non-Gaussian elements, and that way I'm only benefiting from the position suppression and not damaged by the momentum. So, and then if we further compare this with the qubit case, we have a slightly more hardware efficiency in the bosonic case because even 2 bosonic modes are sufficient to suppress the error. But then what's not nice about this is that we only have a constant factor suppression instead of the quadratic suppression. So although we have a slight more hardware efficiency, the error correcting capability is not as good as the qubit case. So I then went one step further, and then I try to have the same quadratic suppression by using some other technique. So what's really nice about the bosonic system is the bosonic system is infinite dimensional, and we have a huge diverse set of gates that we can implement on the bosonic system. So instead of just using the C0 gate, I decided to use 2-mode squeezing. So in the bosonic case, we can squeeze the states, and that's what's distinguishing bosons from qubits. So what we gain from this 2-mode squeezing is basically we started with some uncorrelated independent noise, and what this 2-mode squeezing is doing is it converts an uncorrelated noise into something very much correlated. So especially when we have an infinitely strong 2-mode squeezing, in this infinite squeezing limit, we have the perfect correlation or perfect anti-correlation. So by using this 2-mode squeezing, we can basically correlate the data and the ancillary almost perfectly. So this means that what this means is if we measure the ancillary noises, it directly tells almost everything about the data noise because they are perfectly correlated or anti-correlated. So ideally, one might want to increase the 2-mode squeezing to infinity because then they are perfectly correlated. But we are not allowed to do that because if we remember how the GKP state works, we can only measure position and momentum simultaneously if they are smaller than square root 2 pi. So what we want to do here is we want to increase the 2-mode squeezing to have a stronger correlation, but we don't want them to exceed what we can measure. So there can be some optimization that we can do to this squeezing parameter. And intuitively, if we start with something very small, we can amplify it further until we reach what we can measure, the square root 2 pi. And if we start with some large noise, we cannot amplify too much because then the errors are exceeding what we can measure. So I did this optimization, and basically what this scheme ends up giving us is we can start with some initial noise, and we can quadratically suppress the noise up to some small logarithmic factor. So now by replacing the C0 gate with some tumor squeezing operation, I can still use only 2 bosonic modes, and I can now suppress both position and momentum noise quadratically, like 513 code would do. So I still have this hardware efficiency, and I can also do quadratic suppression. So that's really nice, but the subtle difference between what I found and what 513 code has is here the type of error that I can correct is specifically the random displacement noise, whereas in the multi-qubit case, we can correct arbitrary errors. So I have less flexibility in the type of the error that I can correct, but if we really have that sort of error, we can have the same quadratic suppression and we can do it in a more hardware efficient way. So those are the small example that works really nicely, and moving further on to how we can potentially generalize this. Basically, we can use any Gaussian operation to entangle the data qubit with the GKP states, and this basically lays out the entire general formalism on how we can do useful bosonic error correction. So instead of using, say, position eigenstate to define some bosonic stabilizer code, we are using this non-Gaussian resource to define something actually can correct error. So this defines the entire GKP stabilizer codes, and one can play with many different encodings, many different Gaussian operations to define some interesting code. And what's really nice about this is because the non-Gaussianity is only in the input state, and we only need to do some Gaussian operation here. When we want to do some logical Gaussian operation, we can just undo the encoding and then do the gate that we want to have, and then redo the encoding. So in principle, any logical Gaussian operations can be implemented by physical Gaussian operations. So this way, we have the same nice property that qubit stabilizer code have. So that was the general structure of the code that can that we can have out of this formalism. So the natural open questions are whether there is a nice class of Gaussian unitaries that actually can define some fault-tolerant variant of this code. So that could be one open question that we can think of. And the other questions is, I only consider the smallest code, but whether there is some locally implementable bosonic code like this fashion. That would be, I think, another interesting thing to look into. And then we can also think about whether this is suited with the current technology. And I also talked about the Gaussian operations, so I think that's also an interesting thing to look into, whether we can do some non-Gaussian things with it. And like I said, what I came up with here only works for random displacement errors, so I think it's also worthwhile to think whether we can also correct non-Gaussian errors. So with that, I'll conclude here, and I thank you for your attention.
Okay, time for questions.
So as we probably know that the bosonic mode itself has its own noise channels, right? So have you considered that with the with the noise channels of qubits and oscillators? So if I have two oscillator qubits and then 2 bosonic mode oscillators, then how does it compare in terms of arrows?
So I'm not sure if I understood the question correctly.
So
yeah.
you are trying to add these bosonic mode as oscillator qubits, right? You're adding a bunch of CNOTs, and then you're entangling the noise information on that bosonic mode, right? So how does the error rates of the bosonic mode propagate compared to the qubits oscillators?
I see. So well, I'm still not sure if I. So anyway, so I'm not directly comparing this bosonic code with qubit code. What I'm trying to compare is whether I have a quadratic suppression or not. So I'm not trying to make a direct comparison. If this answers your question,
okay, sure.
Maybe we can talk offline.
Yeah, I can talk to you.
Could you say a bit more about how you derive codes in this formalism? Do they come directly from qubit codes, or do you have to do something different?
Right. So I started picking the nice qubit code and then just make a direct translation into bosonic mode. So that was, for example, the repetition type code where I was using the CNOT gate. It turns out what's good with qubits may not necessarily be good with bosons. So that's why I needed to come up with, say, tumor squeezing, because there's a lot more we can do with bosons. So I think we should just start from the scratch instead of borrowing the nice Clifford operation from qubit and then translating into boson. I think we should do more than that.
Thank you.
Yeah, thank you.
So the GKP codes take physical bosons and map them to logical qubits, and your codes take physical bosons and map them to logical bosons. Do you know if there are codes that will take physical bosons and map them to, physical qubits and map them to logical bosons?
I'm not aware of that. I don't think there is such a code, but I think that's an interesting class of code that one can explore.
I'm not sure how the dimension counting would work on that one, but I had the question. So in the case of qubits, one of the arguments for why we should focus on stochastic Pauli errors is that when you have a general local map, then the cross operators are projected onto Pauli errors by error correction. Is there a similar argument in the bosonic setting that kind of justifies the noise?
So there is a similar argument that any bosonic error can be expanded in terms of displacement, but that may not be true, especially when we have large energy system, which is another story. But my favorite way to defend my error model is the following. So here in this case, so the usual error model that we carry in bosonic systems are usually photon loss, where we have energy attenuation. And the way I justify my error model is we can simply amplify the photon loss, and we can end up with the random Pauli error that I assume that I have in the system. So that way I can just start with something that I actually have in the lab, and then transform that into what I assume here. So that's my favorite answer to that question.
Okay, thanks.
Thank you.
Okay, are there more questions? Okay, oh.
Yeah, just to add to that, your displacements form a basis for all operators on the Hilbert space. So you take the cross operator of whatever your favorite noise is, expand that in terms of displacements. If it's supported mostly on the correctable displacements, then it's okay. And if it's not, then it's mostly not okay. And this is true for for any type of GKP type code.
So in the regular qubit codes, we can run encoding circuit once and then keep measuring the generators. Does it also work with these codes, or do you have to run the encoding circuit over and over again?
I think here we can also postpone the syndrome measurement later, and then to do some gate, we can just do some encoded version of the gate instead of. So the reason why I showed this inverse of the encoding and then gate and then encoding was just to show that whatever that is a Gaussian operation. We can for sure simplify that depending on the specific code that we have in mind. But yeah, I mean, conceptually, we don't have to decode every single time.
For qubit codes, there's this notion of distance, which is maybe sometimes read too much into as assessing the quality of a code. There's much more than that, but it comes from the geometry of the discrete, space that you deal with qubit codes. What is the analog of distance for these codes, or is there even one?
So I think, unfortunately, there's no analog notion of distance here because I'm suppressing the noise, but I'm not correcting noise exactly. So even though the noises are small, I'm not correcting it all the way down to 0. I'm just making it to something much smaller. So in this sense, this is kind of like an approximate error correction code. But at the end of the day, I didn't care because I have the desired noise suppression anyway. So short answer is there's no notion of distance yet in this type of codes. Yeah.
Thanks.
Thank you.
Okay, so if there's no more questions, let's thank the speaker and